Dear students, welcome back. So today I am going to take up the next class, and in this class I am going to take the forced oscillation, and this forced oscillation I am going to divide into the two part. So today we'll write down the differential equation for the forced oscillation, and then we'll solve that differential equation to find out the value of the displacement, that is how the amplitude is going to vary with the forced oscillation. And then finally we'll also find out what will be the phase of the forced oscillation, right? And then in the second part we'll be saying about the resonance due to the forced oscillation. So today let us look into what is the forced oscillation, something about which we have already seen, and how to write down the differential equation for the forced oscillation. So let's start with. So this is your forced oscillation. Now in this oscillation, here as you can see in this diagram, here you have got one spring, and in this spring we have the spring constant. Here we have taken as the K, and a mass M is attached with this. So let us suppose this is fixed over here, right? And then under this mass here a force is acting. So F equal to M into G, that is the force that is acting, and the spring is oscillating with its frequency, angular frequency, and let us suppose that is your omega naught. Naturally this is called your natural frequency. Now this is your free oscillations. Now what I am going to do along with that, it is already doing your free oscillation, but here you see here one part your S is there and it is your detached. Now here I am going to move this up and down. So here I am going to move up, and then again I am going to move it down. So that is, this spring is being oscillated from the external source. So let us suppose we have kept this in the hand, and from the hand we have started oscillating this spring system. So let us suppose the frequency with which we are going to oscillate up and down, that angular frequency is your omega. Omega naught is your natural frequency, and the external frequency that we are going to provide is your omega. So then what is happening now? This mass here earlier it was oscillating with your natural frequency, and it was giving a particular displacement, and this displacement we had called as x from the mean position. Now if I am going to oscillate with the external frequency omega, and we are oscillating with the SHM, and that SHM is your A cos omega t, where A is the amplitude which you are oscillating. So you are taking A up, you are going to take it A down, and then how much this mass is going to oscillate, right, with this spring. This is what we have to find it out. So let us look into it. So what we say, we deduce a solution for the forced oscillation using the arrangement of the mass on a vertical spring with the spring constant K as shown in the diagram. Here we move the upper and S of the spring up and down harmonically in a vertical direction, and that harmonic oscillations that we are going to give is A cos omega t. Here we have not considered the phase. For simplicity we have taken the phase is 0, where A is the amplitude and omega is the applied frequency. So external frequency that we have applied is your omega. We measure the displacement x from the equilibrium position of the mass and take displacement in the downward direction as positive. So if you are going to take the downward direction, then this displacement will be taken as positive. If you are going to take the upward direction, then that displacement will be taken as negative. Downward direction as positive, and the resultant equation. So now you only imagine what will be the resultant differential equation. Now here this spring is oscillating in a certain medium. Let us suppose that medium may be air medium. So it is going to oscillate in air medium. So naturally here also the damping force is acting, right? It may be the liquid also. So it is oscillating in a air medium or any damp medium, and then we are going to provide some external oscillations also, external simple harmonic oscillations we are giving, and then what will be the differential equation for this? This is what we have to write down. So what we can say, we are just going to apply your Hooke's law. M dA square x upon dt square equal to minus k into x. This was for your free oscillations. You have already seen M dA square x upon dt square will equal to minus kx is for your free oscillations, minus bv it is for your damped oscillation, and now here you have given what additional oscillations A cos omega t. So naturally this has been added. This A cos omega t is your simple harmonic motion that here you have given, right? So now what will be our differential equation? M d square x upon dt square minus kx minus bv, where b is your damping medium, v is the velocity with which it is oscillating, plus a cos omega t. A cos omega t is your external frequency that you are going to provide. Now, so therefore, what we can do, all the negative I have taken on the left hand side. So I am going to form a equation m d square x upon dt square plus kx plus m v equal to a cos omega t. Now here all your symbols have the same thing. So now what you do, you divide all the term by m. So if you are going to divide all the term by m, then what you are getting, d square x upon dt square plus k by m plus b by m dx upon dt equal to a by m cos omega t, where a by m is equal to, we'll taking as f. Now we already know that k by m is called your omega naught square, and that you call natural frequency, right? And b by m is equal to your 2 gamma, right? And how we have taken this v, here you have got the v, and v is equal to dx upon dt. This is what I have written, is equal to a by m. A was your external amplitude over here. By m you have divided all the terms by m. So a by m we are going to take a constant, is equal to a by m cos omega t. So this is your differential equation, and this differential equation we required to solve. Find out the value of the amplitude and what is the phase of the amplitude. So this is what we are going to look into in detail now. That is, we are going to solve this differential equation. So now let us proceed. So before we go on the solution of the differential equation, let us see if you are going to oscillate with a different frequency, external frequency, then what is going to happen. At very low frequency, the amplitude of the oscillations tends to the value of the amplitude A of the point of suspension. What it does mean, that is, here this was your spring, right? And from here you have your spring like this, and here you have attached the mass. This is the mass that you have attached, and this part you are taking up and down here. So this spring you are taking up and down with your angular frequency a cos omega t. So here, if this value of the angular frequency is very small, right, then its amplitude, this mass, is also going to oscillate with the same amplitude a. So whatever the amplitude you are going to give, it will also be oscillate with the same amplitude. That is, this mass is going to oscillate with the angular frequency that you have provided externally. Under these conditions, the motion is governed by the spring constant and stiffness of the spring, of course. If the omega is increased, the amplitude of oscillation increases dramatically as the resonance frequency is approached. So about the resonance frequency I will come later. So what I am telling you is, slowly, let us suppose you are going to increase the angular frequency omega. So as you are going to increase the angular frequency omega, this amplitude, that is the value of the x that we had taken in the previous slide, this value of the x from the mean position is going to increase. So it will come over here. So drastically it is going to increase. Slowly, as you are increasing, this amplitude is slowly going to increase. So it will come over here, it will come over here. From this position, then again it will further increase, it will go there, it will come here. So this is how your amplitude is going to increase as your external frequency you are going to increase. But then you will have a particular limit. Up to a particular limit it is going to increase till you have got the condition of the resonance. So what is the condition of the resonance? That we'll see later. So in between, let us suppose as we are slowly increasing the frequency, we have come to the condition of the resonance. Once you are crossing the condition of the resonance, then further if you are going to increase the angular frequency, the displacement is going to decrease. At the higher frequency still, the amplitude tends to 0 when the motion is governed by inertia of the mass, right? So if you are going to increase further angular motion, then amplitude is not going to increase, rather it is going to decrease. At all frequency, however, the mass moves up and down periodically with the frequency omega. So whatever the frequency you have given, so mass is going to oscillate with the same frequency omega. I am not talking about the amplitude, but it is going to make the displacement with the same angular frequency omega. this behavior suggests that the displacement x of the mass can be written as what we can say d square x upon dt square is equal to, it was your k by m, so what we can say omega naught square plus 2 gamma dx upon dt equal to f cos omega t. And what we require to solve this differential equation, and we require to find out what is the value of x, right? So now here we can say its general solution can be given as x equal to a e power alpha t, or a sine omega t plus phi, or a cos omega t plus phi. You can take any one and you can solve. You can differentiate 2 times or 1 times or whatever is the condition required, and you will have to substitute all those values in the equation 1, and then you have to find out the differential equation. So let us see. Now the general solution that we have just seen in the previous slide, this is the equation that we have got, and from here we have to find out what is the value of the x. So what we can say here, x can be given as x equal to a cos omega t plus phi. So if I'm going to differentiate once, I'm going to get minus a omega sine omega t plus phi. Again, if I'm going to differentiate, what I'm going to get minus a omega square cos omega t plus phi. Now you substitute all this value, that is the value of the x. Here the value of the x, value of dx upon dt, and value of d square x upon dt square in your equation 1. So here what I have done, just I have substituted all those values that you have. But on the right hand side over here in this equation number 1, you see this right hand side. What I have done over here in the right hand side, cos omega t plus phi I have added, or minus phi I have subtracted. So you should not have any problem. The things that I have added, phi I have added, 5 I have subtracted, so it remains the same equation f cos omega t. Why I have done? Because I can use here the formula f cos a minus b, right? So that both the side I can solve this equation. All right. So now the right hand side I'm going to solve. The same thing I'm going to expand on the right hand side. So left hand side I have written the same thing. Same thing has been copied up to here, right? Up to here the same thing has been copied, and right side I'm going to expand. So here what you have, here you have cos a minus b. So cos a minus b, what we can say, cos a into cos b plus sin a into sin b. So cos a, so cos omega t plus phi, right, into plus sin omega into cos phi plus sin omega t plus phi into sin phi. Just I have applied. So now you see cos a, this I'm saying cos a, and this I'm calling as b. This I'm calling as b. So this is your cos a minus cos b, right? Cos a minus b. So cos a into cos b. So cos a is how much? Cos omega t plus phi. Here we have taken cos omega t plus phi into cos b cos phi. Again sin omega t plus phi into sin phi. Just I have applied the formula. Now what I'm going to take on the left hand side, in the left hand side of this equation, cos omega t plus phi I have taken common. Wherever you have, you take it common. So cos omega t plus phi I have taken common. So what I'm getting here, the one term that I'm getting is minus a omega square. So minus a omega square I have written over here, and cos omega t plus phi is here also. Cos omega t plus phi is here also. Here you have plus omega naught square a, so that I have written over here, right? This I have written as it is, minus 2 omega 2 gamma sin omega t plus phi, as it is I have written, right? And this also I have as it is I have written, right? F cos omega t plus phi into cos phi plus sin omega t plus phi into sin phi. Now what I'm going to do is I'm going to equate the cos omega t plus phi and sin omega t plus phi on both the sides. So above equation is true solution, then at any time the coefficient of the sine and cos on both sides must be the same, right? So this two side, that is equation number 5, you look at this equation number 5. If the value of the cos omega t plus phi, right, and sin omega t plus phi is same on the both the side, then only what we can say, this equation is correct. If it is not so, then we cannot say this equation is correct. So therefore, if I am going to equate, then what is the coefficient of cos omega t plus phi on the left hand side is your equal to omega naught square a minus a omega square. This is your left hand side, right? And right hand side is your f cos phi, because it is multiplied by f, so it is f cos phi. Similarly, you can take of your sine phi. Again, you can equate the sine phi that in your next slide. So what I have done, I have equated the coefficient, and after equating the coefficient, this is what I told you: omega naught square a minus a omega square equal to f cos phi. And similarly, the coefficient of sine phi is equal sine omega t plus phi is on both the sides was equal to your 2a omega gamma f sine phi. So now what we do, we have to find out what is the value of a. What is the value of a? That is going to give you the amplitude. So what do you do? Square and add both the sides. That is equation 6 and 7, and solve it. So if I'm going to square and add, then it is your a square omega naught square minus omega square whole square, because this a I have taken common, so it becomes your a square, and naturally plus 4a square gamma square omega square is equal to f square, because cos square phi plus sin square phi is equal to 1, so it is your f square. So this is how I have calculated the value of a. So the amplitude of this motion is going to be f square, right, upon minus omega naught square minus omega square plus 4 gamma square omega square. So the value of a, the value of the amplitude, is this value that we have got. So this is the amplitude. This is how the amplitude of the vibration is going to vary. This is nothing. This amplitude is also just like your x. So this is how the amplitude is going to vary. Naturally, this amplitude will have a certain phase also. So what you can do, you can divide the equation 6 and 7. So after dividing, what you are getting, tan inverse 2a omega gamma upon omega naught square a minus a omega square. So this is the value of the phase that you are getting between your amplitude. How this phase is coming, that will look into in detail maybe in the next class. So this is your solution of the differential equation. So what we have done, we have written the differential equation for the force oscillation, and we have solved that differential equation. Now I will have to critically examine this, that is how this amplitude is going to vary. So this is the mathematical equation that we have got, but we have not critically analyzed this. That is, if the angular frequency, the natural frequency, and the force frequency is going to change, if they are going to become equal, if it is your undamped medium, that is the value of the gamma is going to be 0. So all those things we have to analyze in detail, and that will look into in the next class. So therefore, in the next class, after analyzing this, I will take you some engineering applications of how does, if the omega is going to vary, and omega naught is going to become equal, the value of the gamma is equal to 0. So then how all those things is going to happen, and then what are the engineering applications of this, all those things will be taken up in the next class, and it should be a bit exciting, because the example that I had given you, that the Tansen was playing his musical instrument, and the glass ceiling used to break. So that is nothing, that is the condition of the resonance. So how does the condition of the resonance will come, all those things we'll discuss in the next class. Thank you very much.